Well, the title of my speech is about the efficient laser-based particle acceleration in the so-called bullet and bubble regime. And we achieved that by using a G-class, Joule class, ultra-short pulses. Well, okay. So the motivation here is that we need some, in some applications, we need high energy electrons. These applications are in our examples are related to nuclear thermology and nuclear reactions. So in that sense, we get used to use wake field acceleration, which provides mono-energetic bunch of high energy electrons up to giga electron volts levels. But the problem here is the wave field acceleration uses low density plasma, much less than the critical density. So for achieve high levels of charge, the alternative we use is the relativistic self-trapping regime. So the self-trapping regime is well established since the 1960s. And by now, even the relativistic self-trapping make use of the of commercial lasers that are already available. Let me try to explain a little bit about the relativistic self-trapping regime. So in the standard scheme of laser plasma interaction, we got a soliton-like structure moving in the plasma. And we have two extremes cases. The first one is when the this soliton structure is filled completely by light, and the other one is when the cavity is filled only in the front part of the cavity. So our goal here is to identify the most efficient regime of relativistic self-trapping. So for doing that, we perform a three-dimensional particle in cell simulation. Here we provide the parameter we use. And let me know that we use a constant range of the laser energy, which is 2.2 joules. And we vary the pulse duration from 6 femtoseconds up to 20 femtoseconds, going by 6, 10, 15, and 20 femtoseconds. By doing that, we also vary the electron density, the dimensionless amplitude of the field, and of course the intensity. Okay, so let me talk a little bit about matching conditions here. So by now, some consensus has been reached about the dependence on the size of the cavity related to the parameters of the laser and the plasma. So you see the results of this work. I think this work was presented today or yesterday in the morning. But here we use actually these matching conditions, which is in concordance with our results. And well, one thing of the relativistic self-trapping regime is that unlike the self-trapping, the non-relativistic trapping regime, here this regime is affected by by instabilities. So in order to avoid instabilities, we make use of the condition that the length of the pulse, t tau, with tau being the pulse duration, must be less than the relativistic plasma wavelength. And the other condition is the size of the cavity. Oh, okay. So the size of the pulse must be also less than the size of the cavity. Okay. Keep if we keep going with the matching conditions, we also can provide some qualitative values of our simulation. But well, here we see the formula we made use in our simulation. So here we use the energy that the electron acquires in the field, which is related on a dependence of the electrical field and the length on which the laser pulse is exhausted. This gives us energy conversion efficiency, which is the relation between the energy of the electrons and the energy of the laser. And it gives us a result of tens of percent of the energy laser. But these kind of formulas are available. They don't pretend to be exact formulas. So we need, in this case, to compare with the numerical simulation. The effective here for the case we have studied give us real dependence on the pulse duration of the effective of the coefficient of conversion for electrons of cutoff starting from 15 mega electron volts, and this the second one is related to 30 mega electron volts. And we see that the dependence is that the conversion efficiency goes down by increasing the pulse duration. They reach a maximum on about 10 femtoseconds. And actually, they are on the same level for the bubble, which is represented on blue color, and the laser bubble, which is represented on red color. Different situation may be happen with the coefficient for high energy electrons. So we see some advantage of the use of the bubble in terms of the energy conversion efficiency. But for the characteristic of the total charge, we see that the laser bullet, represented again in red, is always higher, and the difference is actually potential here. We see a monotic decreasing of the charge depending on the duration. For this cutoff of 15 mega electron volts and 30 electron volts, but the case may be different from short pulses, from the cutoff of high energy electrons. This could be explained by using some analysis of a single particle analysis here, and we get the in this case what happens, the electron entering the region of acceleration in the case of the bullet regime get immediately accelerated also by the field of the laser pulse. In the case of what does indicate as the spectre is that for the laser bullet regime, we see a plateau form spectrum, and for the bubble regime, we see trying to get a mono-energetic form. The intermediate part of this relativistic cell trapping regime varies from the top of the calculation, which are in this case for the charge for the bullet, and the minimum, which is given by the the up is from for the laser bullet, and the down mark is given by the bubble. We try to get some principal conclusions here for electrons. So here we demonstrate that if we use current existing lasers, the optimal option is to use the laser bullet regime. But some cases when we need high energy electrons with low density, better way maybe the bubble. Although here the problem is that in order to reach short pulses for the bubble, we need special techniques for shortening the pulse, which may bring us to some losses. And the last part, my last slide, is the next stage of our research, which is about proton acceleration. And having known that the bullet is the optimal way to get high energy electrons at the high total charge, we can make use of this regime to analyze the proton output of this. So in this case, we study the we study the explosion of this bubble in gas jets targets. And we get, well, maybe two or three reasons of the acceleration of protons from the edge of the plasma. They may be related to direct column explosion. Also, they may be related to electrical solenoidal field. So in order to analyze this problem, we have performed Helmholtz fields, the composition of the field, and actually we have seen the primary contribution of proton accelerations come from the electrostatic component. The solenoidal part plays a role at the initial stage of acceleration, but actually it lost a lot of importance at bigger times. So that's all. Thank you.
Thank you very much.